So let's get started. Now we introduced matrices by saying that they will generalize numbers, but what exactly does that mean? So I'm not going to give a precise definition of what generalization means, but here's some nice to haves from a generalization. For me, numbers only make sense with the operations defined on them, because we can add them or multiply or divide and so on. We want to carry these operations over to the new setting such that when we restrict it in a particular application, we recover arithmetic as we know and love. That's the important quality to have, that we expand this notion, and when we look at a special case, we recover what we had. And hopefully, when we generalize, when we expand the context of definition, the identities are preserved. And by identities, I mean x plus 0 is x, and x times 1 is x, or associativity properties. So associativity of addition, for example, says if we add a to the sum of b and c, it's the same as taking the sum of a and b and then adding c. Or you might want commutativity, for example, where a and b is equal to b plus a for any numbers a and b and c. Is that the case with matrix arithmetic? We should check as a sort of coherency check that we recover what we expect. Now, remember, last time we had this example that if x is a number, then the one-by-one matrix of x should reflect faithfully the familiar properties that a number has. So that's the special domain that we're going to be restricting our definitions to. Now we can try generalizing from that, 2 plus 3 equals 5, for example. So if we had 2 plus 3, I hope it's going to be equal to 5. Or more generally, if we have x plus y, it's going to be equal to the one-by-one matrix whose component is x plus y. How do we generalize from here? Well, one way that's cheap and lazy is to say if you have two components now, and you add to it a vector with two components, you end up with a vector with two components, and their components are just defined as the sum of the corresponding components. That's pretty nice, pretty cheap. You get to piggyback off of addition of numbers in many ways. So let's try that as our definition. So to start with, we have A and B are both m by n matrices. It's important that they're the same dimension. We define, in that case, matrix addition of A and B to be the m by n matrix A plus B, which has components C sub ij, where C sub ij, the components, the ijth component of the sum is just the sum of the ith j component of A and the ith j component of B. Right? That's what we were doing before. Now, let's see an example of this. If we have A be a height by weight 2 by 3 matrix, 1, 3, 1 in the first row, 2, 0, 6 in the second row, and B is a 2 by 3 matrix, 1, 1, minus 1 in the first row, 2, 3, pi in the second row, then a plus b is equal to, let's see, well, the first component in the first row is 1 plus 1. The second component is 3 plus 1. And the third component is 1 plus minus 1. So that's 1 minus 1. Now, second row, it's 2 plus 2. The next component in the second row is 0 plus 3. The last component is 6 plus pi. And we can evaluate each of these. So 1 plus 1 is 2. 3 plus 1 is 4. 1 minus 1 is 0. 2 plus 2 is 4. 0 plus 3 is 3. 6 plus pi, well, that's as good as it gets. And we could take a decimal approximation, but I'm not going to bother. So this is the defining quality of matrix addition, that the result is just adding up all the components, component-wise. Now, let's see, here are some properties that we like from usual arithmetic. I'm going to have the lowercase letter sub ij be the ijth component of the associated matrix. So for this, if you let d equal to b plus c, so it's equal to dij, which is equal to bij plus cij, then a plus d is equal to aij plus dij, which is just bij plus cij, right? Now we combine them into a single matrix, aij plus parentheses bij plus cij. And this is where piggybacking off of the usual arithmetic operator of numbers comes into play, because this is a number, that's a number, that's a number. And we know that associativity holds for numbers. So we know definitely that aij plus bij plus cij gives us the same thing, right? But then unrolling the definition of matrix multiplication, this is just aij plus bij plus cij. And unrolling it again, this is just aij plus bij plus cij. And we recognize these are the components for a plus b in parentheses plus matrix for c. So we have then established associativity of arithmetic. The next nice to have is commutativity. And this is just checking that the result of adding a and b component-wise is just a matrix whose components are the sum. But then, since this is just the sum of numbers, we can use commutativity. Now, it's important to note we are just swapping the order of adding these numbers. We are not swapping the indices. The indices are the same. Since we've swapped b and a, we can undo the matrix addition to get precisely the sum of the matrices, and we see, yes, indeed, a plus b is equal to b plus a. Now there's one last property that is also nice to have, that there's a zero matrix. Namely, the ijth component is 0 for every component. And if you look at the matrix addition of the 0 matrix plus A for any A, this is just 0 plus Aij by definition of matrix addition. And then by the definition of 0, 0 plus anything is the other thing, so that's just Aij. And this is unrolling the definitions, just the same thing as 0 plus A is equal to A, precisely as desired. So that's nice. A lot of the properties that we really take advantage of when doing arithmetic also hold for matrix addition. So that's a very nice generalization. So, well, before moving on, just one last thing. If n is a positive integer, and we have something like a plus dot 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 plus a, we do that n times. Now, if this were a number, remember, we learned in grade school x plus and so on plus x n times is equal to nx. We would like to generalize this property now to matrices. And if we unfold this using the components, well, then we just have this for each component. So we have this, multiplying every component n times. So we're adding the matrix A to itself n times. It's the same as multiplying each component of A by n. We want to generalize this property of addition to some appropriate notion of multiplication. And we can do that. So we will do that. It's called scalar multiplication. Scalar multiplication sounds scary, but scalar is a fancy word for not a matrix. In our case, just a number. So if you let C be a number, you let A be an m by n matrix fixed, then we define the scalar multiplication of C with matrix A to be, and we write it just C times A. It's equal to precisely what we just had, C times Aij. That's it, nothing terribly fancy. So let's see a few examples of this. So 3 times the matrix with all the ones everywhere except in the lower left corner. And this is the same thing as multiplying every component by 3. So 3 times 1 is, that's right, 3. And similarly, 3 times 1, 3. 3 times 0, yes, 0 times anything is still 0 here. And 3 times 1 is 3. Now, 7 times this matrix is, 7 times 1 is 7. 7 times 6 is 42. 7 times minus 1 is minus 7. At 7 times 2 is 14. And this can be any number with scalar multiplication. So the square root of 2 times this matrix gives us a matrix. Square root of 2 squared is 2. Square root of 2 times 1 over square root of 2 is 1. Square root of 2 times 1 is square root of 2. Square root of 2 times 0 is 0. So that is the last example. Now, why is this scalar multiplication exactly? If you remember from last time, we introduced a notion of a scalar matrix, where all the diagonal entries are the same value, and all the off-diagonals are 0. So effectively, what we do in this case is we say, okay, you let I be equal to the diagonal matrix with just ones. And we sometimes write this to indicate, yes, it's just a diagonal matrix, and here's the entries along the diagonal. All other entries are 0. Then a scalar matrix, as we have defined it, is just A times scalar multiplication, I, the identity matrix. That's the connection between a scalar matrix and scalar multiplication. So that's good. We're seeing where some of this terminology is coming from. But just as last time, when we introduced matrix addition, we had these coherency checks. We could do something similar with matrix multiplication. For example, it's not hard to show that 0, the scalar, times A, any m by n matrix, is 0, the m by n matrix. Right? And if you're not sure how to see that, just write out every component of A, then multiply it by 0. You end up getting all the components vanishing in the resulting matrix from that product. And similarly, if you do 1 times A, it's equal to A. And there's some other consistency checks, like 1 times A is A, minus 1 the number, times A, then add A is equal to the 0 matrix. What else? We have distributivity, so scalar multiplication distributes over addition. So this is the same thing as the scalar product of A and big A, little a and big B. What other examples could we think of? Scalar multiplication also distributes over scalar addition. So this is the same thing as little a times matrix A, little b times matrix A. And again, this is just because we're piggybacking off of how we're defining matrix addition, using the addition of numbers. So, wow, that's gone on a long time. I better end it here. We'll continue with trying to generalize multiplying numbers to matrices next time.